Welcome to springlib.
Hi, let us imagine we have three gears A, B, and then the smallest one C. So they are in decreasing sizes and they have a rod running through them, through their centers. Well, this one is not exactly at center, so let me just make it more centric. And then the radii are RC, RB, RA. And then let's imagine this disk is moving with an angular velocity omega A, that is A, and then we have to figure out what is omega C, and point A is fixed. B and C are free to move. So as we have been doing in this chapter, and this is the last problem of this section of this chapter, we break the motion into translation and rotation. So since A is fixed, the translation velocity for A, Vt, equals 0. For rotational motion, if this is our center and this is the point of contact, then the velocity, if this is moving clockwise, it's going to point the other way, not this way. It's going to point here, and it's going to be omega A RA. So the net motion is just going to be due to the rotational velocity omega A RA. Now, for gears, or in fact for any motion without where rolling without slipping is happening, point of contact has velocity equals 0. So let us call this point as AB, which is the point of contact between A and B. So it's unconventional to denote 2 points by a point by 2 letters, but let's do that for understanding, because it's point of contact between A and B, or maybe let's call it PAB, point of contact between A and B, PAB. Okay, then so now let us look at what is the velocity at PAB due to motion of the rod and the disk AB. It's a compound, it's a rigid body motion. So let's assume this is our rod, and let us assume this is moving anti-clockwise. Again, if we assume wrong, we'll get a negative number, which will give us the correct direction if assumed direction is wrong. Anyways, we'll assume it to be anti-clockwise. So point A is fixed. So this is fixed. So what are the other velocities? So at point B, this is going to point like this, and the value will be omega ABC, then RA plus RB. Now for disk B here, this is actually like a translational velocity because the motion of the center, so all the points will have the same velocity added to them. So this point PAB will also have velocity omega ABC RA plus RB. Now this disk B is also going to rotate, right, because it's on a gear. So let us, if this disk A is rotating clockwise, let us assume this is rotating anti-clockwise, and well, let's just only draw it on the disk, not on the rod. And this is omega B. So if this is omega B, then, well, let's draw it in a separate diagram. So let's call this some sort of translational diagram, which is not translational, like let's call it T prime, because we have written down the velocity of disk B because of the circular motion of the rod ABC. But for disk B, it's translational. So let us call it translational for B. And then rotational for B. At point PAB, so at center, obviously the rotational motion, let's assume omega B to be anti-clockwise. At point AB, it's going to point like this, and value will be omega B RB. So the net motion, and also we are concerned with point BC as well here. So let's analyze this point as well, like while we are doing all the other calculations. So at this point, the rod will have a velocity omega ABC RA plus 2RB. This is the velocity at this point, at point B, point of contact between B and C. And the velocity here, because of the rotation of B, it's anti-clockwise, so it's going to point here and going to be omega B RB. Okay, so the net motion we get at PAB, this is omega B RB in this direction. So this is PAB, and then in this direction, omega ABC RA plus RB. And at this point, PBC, the velocity contributions from the rod and the circle are in this direction. It was for the rod, omega ABC RA plus 2RB, and we also get a contribution again, adding vector head to tail. This is omega B RB in this direction again. And yeah, that's all. Rotational motion of B, and then the motion due to rotation of the rod. Which in fact, right. So rather than complicating everything, let's rethink our strategy. So rather than writing the contribution of rod here, let us just take the contribution of rod to be at the center, which is omega ABC RA plus RB, pointing like this, which is the same translational velocity. So this point will also have the same translational velocity, omega C RA plus RB. So let's call this VTB equals this, and then all these three arrows are VTB. So that we don't double count this, right? So it's all VTB, right? And then the rotational velocities are pointing like these. So then, yeah, so then the final diagram should be easier. It's not going to be this complicated. So we were double counting things. So now we have corrected for that. So point B is definitely moving with VTB. Point BC, the point of contact between B and C, due to the motion up to this analysis point. So here we get omega B RB, and we also get VTB, which is omega ABC RA plus RB. And at point of contact AB, we get VTB, which is omega ABC RA plus RB, and then the rotational velocity omega B RB. Okay, now for the third one, so the third disk, omega C, is smaller disk. So this is again connected to the rod, and for rod, point A is fixed. So the center of this circle C is going to have velocity VTC, the translational velocity of C. This is going to be omega ABC, and now RA plus 2RB plus RC. That's the distance up to this point. So because there were other circles, right? Remember? So this will be 2RB, then RA. So the total distance here. So then this is the correct way to do it. I was trying to include this in the earlier point C, but that was not the correct way. The correct way to analyze the motion of a circular disk is to find the motion of the center and then find rotational velocity at each point, and then add the velocity of center to the rotational velocity at each point. So that's the correct way to do it. So we have found the velocity of center. So all points are going to have the same velocity for translational part because it's a rigid body. So all points share this velocity. So VTC, VTC. And then the rotational motion tells us, well, here we have no point of contact, so we're not going to analyze this point. But here, PBC, we are going to analyze. So it's PBC. We have VTC, which is omega ABC RA plus 2RB plus RC, and then omega C RC. And we have assumed the motion, actually let's assume the motion to be clockwise. So what will happen is that this velocity, rather than pointing here, this will go and add here as omega C RC. So these two velocities will add. So, well, yeah, I'm not writing the net velocity. So let me just write rotational. Sorry, went ahead of myself. So for rotational velocity, let us assume omega C to be clockwise, and then this will be omega C RC. And then the net motion due to circular motion of C is going to be omega C RC. And then the translational motion VTC, which is omega ABC RA plus 2RB plus RC. Okay, now we know that the velocities of V at PBA has to be 0 and V at PBC have to be 0 because they are points of contact. So, and for gears and for rolling without slipping, points of contact must have net velocity 0. So writing down the velocities for PBA, the net velocities for PBA, let us see what do we have. So from disk A, we have omega A RA. So we get omega A RA, and then from the motion at B, we get omega B RB in the same direction. So plus omega B RB, and then in the opposite direction, we have omega ABC RA plus RB. So omega ABC RA plus RB. This is equation 1. And then for point, so this is setting V PBA equals 0. So this implies this. So V PBC equals 0. What does this imply? So due to disk B, we have net motion at point C, which is omega B RB, then omega ABC RA RB in one direction, which is pointing towards up. So omega B RB plus omega ABC RA plus RB, right? And this has to equal, okay, well, not equal, but what we have shown is that according to our assumed omega, it turns out that all of them are pointing along the same direction. So one of them has to flip. So we'll see which one, but we'll just write it down for now. So the net velocity has to be 0. So since they're all pointing along the same direction, we'll write plus omega C RC omega ABC plus omega C RC plus omega ABC RA plus 2RB plus RC. Yeah, so they are all in this, according to our assumed direction, they're all in the same direction, but we know that the total velocity has to be 0. So they all add up, but they all add up to 0. So this automatically tells us that one of these angular velocities have to flip. So let us analyze which one has to flip. So, and the question also asked us to show that omega C is actually independent of radius of gear B. So we have to find omega C eventually. So let us see what we can replace. So RB, so let's solve for RB from 1. So 1 implies omega A RA minus omega ABC RA equals omega ABC minus omega B RB, right? Yes. So RB can be given in terms of omega A RA, sorry, omega A minus omega ABC times RA divided by omega ABC minus omega B. So we have figured out RB, and then let's put this RB in equation 2. So then 2 implies omega B times omega A minus omega ABC RA divided by omega ABC minus omega B plus omega ABC RA plus RB is going to be, let's just take RA common. So this is 1 plus omega A minus omega ABC divided by omega ABC minus omega B, and then plus omega C RC plus omega ABC RA plus 2RB. So again we can take omega RA as common, and then this will become 1 plus 2 times omega A minus omega ABC divided by omega ABC minus omega B. So this is RA plus 2RB and then plus RC equals 0. So let us simplify that, and then we can get an expression for omega C in terms of omega A, omega B, and without any RB into it. So where do we have omega C here? So let's see, we'll separate only those terms. So we have omega C here. So that's the only thing we have. So we should take everything to the right. So just making sure everything is correct. Yes, I think everything is correct. Okay, so then omega C is 1 over RC, and then everything comes to the left. So it's omega B times omega A minus omega ABC RA divided by, let's put a minus here for all of the terms, omega ABC minus omega B plus omega ABC RA, and then this on the top it will be omega ABC minus omega B. So omega ABC and minus omega BC cancel, so you are left with omega A minus omega B divided by omega ABC minus omega B, and then finally plus omega ABC RA, and then denominator is all omega ABC minus omega B, and then on the numerator we have got omega ABC, then minus 2 omega ABC, so there will be a minus omega ABC, then we have 2 omega A, and then we have two omega A minus omega ABC, and then minus omega B as well. So wait, so RA, yeah, there was, the dimensions are wrong here, so I'm just trying to check if I collected all my terms correctly. So RA plus 2RB, so yeah, the bracket should have finished here, and then we have plus RC. Okay, so the bracket finishes there, and so 2 omega C minus omega B. Yeah, I think this is correct. And then finally we have plus omega ABC RC. So all these terms have omega B OBC minus omega B. So let's just add all of them. We still have minus 1 over RC. So omega, so, and finally we have omega B, omega A, RA, sorry, omega B, omega A, RA, minus omega ABC, omega B, RA, plus omega ABC, RA, omega A, minus omega B, omega ABC, RA, plus 2 omega A, omega ABC, RA, minus omega ABC squared, RA, minus omega B, omega ABC, RA, and then all of this divided by, let's absorb this minus sign in the denominator. So it's going to be omega B minus omega ABC, and then all of this, and then plus omega ABC RC. Actually, sorry, so 1 over RC was there, so 1 over RC will come here. That's why checking dimensions is good. So RC has to cancel, so this will be plus omega ABC. Everything should have units of omega. Okay, finally 1 over RC. Then let's see what terms have cancelled. So are there cancellations? Well, we have additions because we have one of this and one of this, so they add, and then, well, they also add omega ABC RA. Was there a minus I missed? Because it would be so much easy if I could cancel these rather than them getting added. Then I have minus omega B ABC RA, minus omega B ABC RA, minus omega ABC omega B RA. Oh, maybe they don't. So yeah, I think it's fine. So we get additions of all of this. So we get 3 times this is some expression. So omega B omega A RA, sorry, no, this is only one of them. So what has added is omega A RA omega ABC. So 3 omega A RA omega ABC, and then minus 3 times again omega B omega ABC RA. That is fine. And then we have remaining terms. So how many terms we have absorbed? So we have added 2, and then this 1, and then we have 1 2 3. So we are left with 1 2 3 4. We have covered 1 2 1 2 3, so 5. So we have total 7, 1 2 3 4 5 6 7. So we have 2 terms left, so which are plus omega B omega A RA minus omega ABC squared RA. This is one term, and this is plus omega ABC. So this is the expression for omega C. It's somewhat complicated, but we have shown that omega C does not depend on RB. And it only depends on omega B. So again, slightly cumbersome expression, But as long as you follow the principle of translation and rotation and equating net velocities, you can always solve these kind of problems. Oh, by the way, there was, yeah, sorry, a denominator here, omega b minus omega abc. Okay, so this is how you solve these kind of problems, and this chapter is finished with this was the last problem, and it was quite a problem. So I hope you like the solutions, and you can check out other problems I solve, and you can contact me with my contact, or I think there should be some messaging services enumerated, and I have to hear from you if you look at these problems, and if I have made mistakes, which are possible. Maths and physics do involve making mistakes. It's part of life. Then we can discuss that. Thank you.